oh, part A is from Unit 1, Part B is from Unit 3, Part C, that kind of thing. All right, so it's generally going to follow the pattern um, of the progression of the course, where you'll see the first question will be more of your descriptive statistics, and the last question will be the most involved question, most likely an inferential sort of deal. But uh, I can show you what there's this. I don't know if it's a company or whatever. It's Stat Medic. They do some review stuff for the exam, and every year they make a prediction of the type of questions that they think are going to be on it. I'm just looking real quick to see if I have it handy, but there it is. So I'll post this up on the on Schoology in a little bit, but for now, I'll just give you a quick look. Assuming, yep, there we go. Save the downloads, and well, it's super tiny because I did a screen grab, but this is what they predict will be on the free response part of the exam. All right, so if you follow what we're about to do, you'll see that it's pretty consistent with this under normal circumstances, but this is what they think will be on the exam based off of previous iterations. So one variable data, two variable data, describe distributions, describe relationships, scatter plot. So that's like, is it a logarithmic regression? What kind of fit are we talking about? If it's one variable data, then it could be just a matter of skewness. So how is the data organized? Is it normally distributed? Is it skewed in one direction or the other? Is it multimodal? So more than one hump. Like the normal distribution has just a single hump, right? But sometimes you could have two humps. You could have three. You could have 20. If there are 20, then it would have to be a huge data set, but you get the idea. So just making a description or an analysis of the type of distribution. Experimental design, are we talking simple random sample, stratified, and all that good stuff? How do you conduct a study? So I give you some background information. Like when we did an assessment on this, I'd give you some background information, and then you'd design the study with that tree diagram that we used, to break off simple random sample into two categories: control, experimental. How are you going to randomly assign? Is it going to be a simple random sample? Is it going to be something else? Right? Sampling distributions probability. All right, so that's more than just a quick blurb. So that we'll talk about that a fair amount as we go forward. Significance test. They think it's going to be a one sample t-test for the mean. Could be matched pairs, but we got to be prepared for any possibility. It could be a two population proportion z-test. That's one of the reasons why we studied those formulas. All right. Confidence interval question, probability. Is it binomial? Is it otherwise? Know your four conditions for a binomial distribution. Well, there's actually a problem in this free response that we're going to go over that addresses that. But it's, your fixed number of trials, fixed probability, independent events, and two outcomes. And then the investigative task, that's usually like question number 6, in my opinion, is like the whole course packed into one question. All right, so any topic could work its way in there. All right, so you might find yourself running a hypothesis test, but also determining the probability of a particular event occurring. All right, describing the nature of the distribution, things like that. All right, so that's one of those. It's like you do 1, 2, 3, 4, and 5, and you're like, okay, I'm feeling pretty good about this. Now take 1, 2, 3, 4, and 5 and smush it into one question. That's your number 6. All right, sounds very intimidating, but if you break it down into little chunks, it's a whole lot easier. But we'll go over an example like that in a couple. Well, probably not today because it takes a while to go through these, but we will. All right. So on the exam, you're given formulas. Right? If you thumb through the packet, you recognize this. Some of it is obvious. Like, for example, I don't know that they needed to tell you the formula for finding the mean, right? It's very intimidating looking, but it's really just add up all your values and divide by the number of values, all right? The model that's being used to find a linear regression equation, y hat is equal to a plus bx. Again, don't know that you needed to be told that. The R value, yeah, I'd probably want that formula, especially if they're going to make me use it. Right? If they're just asking for a correlation coefficient, you could do it on your calculator, but if it's a free response question, they may ask you, some aspect of the formula. Right? So they'll say, knowing that x minus x bar over sx is equal to 12, and y minus y bar over sy, which is a z-score for an x value, z-score for a y value, what would be the correlation coefficient? So maybe they don't give you the raw data, but they give you enough for you to make a determination on your own. All right? Standard deviation, we haven't computed that in a while, but very, very manageable. The y bar is equal to a plus b times the x bar. That variation of linear regression. All right? So it's in the same neck of the woods, but it's used for a different purpose, and we'll talk about that as we go forward. Finding the b value. Well, actually, the y bar part, that equation, that's really not anything too crazy. It's just the mean of the x variable, the mean of the y variable. If you know what b is, then you solve that for a. That helps you determine. So instead of just putting that off, I figured I would explain it real quick. It's a method by which we can use, or a method we can use to determine the linear regression equation. You got your probability rules, all right, the addition rule, and also a form of the multiplication rule, conditional probability. That's all given to you. For a probability distribution, they tell you what the mean is in terms of a formula. Same thing with standard deviation. They get into the binomial rules, so they'll give you all that, geometric rules. But then, and standardized test statistics, confidence intervals. This is the thing where I kind of look at it and say, well, I guess I'm glad you gave me something, but if you're going to give me something, why not give me all of it? All right. So when we did the quizzes last week on the formulas, we memorized the particular formulas. We didn't just go with the general form. So they give you the chi-squared, so that's nice. But they tell you to find a confidence interval. You take a statistic and add to it or subtract from it the critical value multiplied by the standard error of the statistic. Right? Then they give you a few different variations of the formulas, but not a whole heck of a lot here. All right? So they're giving you the standard error. Parameters are one thing, but if they're giving you a standard error for one population proportion, they're only giving you the one variation of it, right? The case where you can't make a reasonable assumption about the value of the population proportion. So they're not giving you the PQ one, they're not giving you the P bar, Q bar one, the pooled distribution. So they'll give you one, and you just have to know the others, all right? For one population mean, they give you one variation of it, really. So you're looking at this and saying, all right, well, and you can look through the rest, but you're looking at this and saying, well, what about the match pairs t-test? Well, they're expecting you to know that s over the square root of n becomes s sub d over the square root of n sub d, right, for a match pairs t-test. All right. So they give you for two populations, they just give you the standard error, but you need to build your test statistic formula or your confidence interval formula from this information, which is why I wanted you to actually just memorize the formulas, because then you don't have to worry about it. All right. Then you get into the questions, which we'll get into in a second, but towards the end of the exam, or right at the very end, they give you some tables. All right, they give you standard normal probabilities. So standard normal curve. All right. And then they also give you the t-distribution values, all right, and the chi-square critical values. All right. So this is the kind of thing that could be unnecessary, but if you're in a pinch, you could always use the tables here. All right. So what it does is it's basically, if I wanted to find second vars, the inverse norm, for example, with an area of, let's say 0.16. My calculator is going to spit out the z-score corresponding with that, about negative 0.99. All right. What this table will do is if you go around and hunt in the table for something very close to 0.16, all right, so it's going to be in this neck of the woods down here. 0.16 is going to be, where are you, 0.16? 0.1611 is probably the best we're going to get. A little too thick. All right, what that corresponds to is a negative 0.9 on the left column and a 0.09 on the top, all right, the column heading. Put those two together, add them up, negative 0.9, and then, well, when I say add them up, I use that term loosely because you're just adding two negative numbers, even though that 0.09 doesn't seem negative. But basically, the value on the left gives you the tenths place. The value on the top gives you the hundredths place. Put them together, and you get a decimal that can be rounded to the nearest hundredth. So negative 0.99. So you look at that and say, well, that's more trouble than it's worth. We'll just use the calculator. I agree. All right. But some of the older calculators don't have the chi-square stuff in it, which is why I recommend you just use one of mine if you have an old TI-83. All right. But that's what all this table stuff is about. In theory, you shouldn't even need to look at that. They usually give a random number table at the end also. This exam may not have called for that, but I don't know. We'll see. All right, but every now and then they'll give you some random number tables if you need it for a particular question. Sometimes they give it right in the question. You know, that's pretty rare, but you know, like what they'll do is they'll just give you an array of numbers and say use these numbers to determine whatever sample you're supposed to determine. All right, but as far as the questions are concerned, you see that there are a total of 6 questions. They tell you to spend, because you get an hour and a half for the free response. I don't know if you have any experience with AP Calculus. You're probably used to the calculator section versus the non-calculator section. That it doesn't work that way here. That you're allowed to use a calculator for the entire exam. All right. So you get an hour and a half. They recommend that you spend the first hour and 5 minutes, oddly specific, on the first 5 questions, with the remaining time, the remaining 25 minutes for number 6. All right. So that's how they recommend you split up your time. The questions 1 through 5 and question 6, they seem like they're in different parts of the exam. They're all contained in the same parts. So you can bounce around from questions 1 through question 6 as many times as you want within that hour and a half. All right. So you're given the paper, and you can just like, okay, well, I know I'm supposed to save about 25 minutes for number 6, so let me do that. But then if you're worried that you're going to run low on time, just jump right to number 6, get working on that, so at least you have something down on paper. Right. Now, in terms of the directions, you can see show all your work, indicate clearly the methods that you use, because you'll be scored on the correctness of your methods as well as the accuracy and completeness of your results and explanations. All right. So you don't want to write down in norm 0.16. You know, that's not going to get you anything. All right. So if you need to come up with a z-score corresponding with a particular area, you're going to want to draw a diagram, label it up nicely, explain what it is you're looking for, and explain what it is you're getting. All right. You don't want to be in a position where you're just putting down numbers, because that's not going to get you anything. All right. You'll get every question quote unquote right, but then walk away with like a 2 or at best a 3 on the exam, right? Because you didn't do the method, not just the answer. You need to demonstrate knowledge of the method. Now, with question number 1 here, I mean, sometimes the questions are pretty cut and dried. Determine the 5-number summary of the distribution. All right, well, maybe I don't need to write an essay for that one, but just keep that idea in mind, all right? So we need a 5-number summary for this data set. This is a frequency distribution, so stat edit. Some of the questions are going to be so easy that you're like, really? That's all they're asking me to do? But that'll be balanced by questions where it's like, really? I don't even know what it's asking me to do, all right? And you know, it's the kind of thing where you'll figure it out. You just gotta, you can't get, I guess the only term I can come up with here is like sticker shock. You can't just look at it and say, whoa, this is crazy. There's no way I'm going to be able to handle it. You can handle it. You just might have to think a little bit about what it's asking you to do before you get started. All right? This is not one of those questions. Very straightforward. So we get our data into the calculator. It's just asking for the 5-number summary. So you don't just want to list 5 numbers. You want to say what those numbers are. So, marker, minimum, lower quartile, median, upper quartile, and maximum. I know when we did these kind of questions, well, actually everything we do in this class, I tend to do abbreviations. You can't assume that they know what your abbreviations represent. I mean, I think it would be pretty obvious that if I wrote max, that I'm referring to the maximum, but the graders are kind of trained to play dumb on that. Like, I don't know what you mean. Who's max? You know, so just be careful. You know, every now and then you could slip by an abbreviation, but I wouldn't take the chance. All right. So stat, I have my data in. Calc option 1. None of this gets written down. My list is in L1. My frequency values are in L2. So I'm going to tell the calculator L2, and I'm going to go to calculate. All right. You have to hit the down arrow in order to get your 5-number summary. So 5, 6, 7, 8, and 21. Now, they didn't say anything about outliers yet. They will. They'll get to that in the next part of the problem. But you got to look at this, and just based off the graph and even our 5-number summary, that 21 kind of jumps out at you. 5, 6, 7, 8. So we're in the single-digit realm, and then all of a sudden we're at 21. All right. You look to the context to help you make sense of it. This is length of stay in a hospital after receiving a particular treatment. Right? Now, of course, it depends on what the treatment is, but it looks like individuals receiving treatments can typically expect to stay in a hospital anywhere between 5 and 9 days. You have a person who stayed for 12 days and a person who stayed for 21 days. Right? So, you know, aside from why they're staying for such a length of time, you know, putting that and the contextual aspect of it aside, there is a number that's way off the beaten path here. Right? So I'm suspecting that that's an outlier, but we'll see. Right? Because in the next part of the problem, they define 2 methods that you can use to determine outliers. Right? Method A, method B. Method A is our standard approach for finding outliers. LQ minus 1.5 the IQR, comma UQ plus 1.5 the IQR. But they also allow for method B, which is the 2 standard deviation rule. So that's the usual, unusual intervals. So anything within 2 standard deviations of the mean is considered to be the usual values. Anything beyond that would be unusual. All right? They're allowing for that level of unusualness to also help determine any outliers. All right? So when they say the 1.5 IQR rule, they're saying LQ minus 1.5 IQR, comma UQ plus 1.5 the IQR. square brackets. All right. So the LQ represents the lower quartile. The UQ represents the upper quartile. What I'm going to do is I'm going to go back to my previous problem and make a note of that. LQ is my lower quartile. UQ is my upper quartile. All right. So that I'm making it crystal clear that anytime I use LQ, this is what I'm referring to. All right. Also, I need those numbers anyway. So we're looking at 6 minus 1.5. The IQR is the upper quartile minus the lower quartile. So 8 minus 6 is equal to 2. So I'm taking 6 and subtracting from it 1.5 times 2. Then I'm taking 8, adding to it 1.5 times 2. All right. Run the numbers. 2 times 1.5 is 3. So 6 minus 3 is 3. 8 plus 3 is 11. Any number beyond this interval would be considered an outlier. Any number beyond 3 to 11 is an outlier. Therefore, well, there's two numbers that are beyond, on the high side, the 11. We don't care about the low side, because there's nothing less than 5. So my outliers would be 12 and 21. Therefore, 12 and 21 are outliers. By this particular method. All right. You tell us the mean length of stay is 7.42 days, which is what we would have computed anyway, with a standard deviation of 2.37. So they rounded, which means that we have license to use their rounded values. Using method B, which is x bar plus or minus 2s, which really amounts to x bar minus 2s, comma, x bar plus 2s. Got to run those numbers. 7.42 minus 2 times 2.237. And then the same values, just with a plus sign. That's going to give us the set of usual values. All right. So I have all these numbers stored in here. I could use the unrounded form, but like I said, they gave us the rounded values, so we'll use their values. So 7.42 minus 2 times 2.237, 2 point, just the 37, not 237. That gives us the low bound. Second enter, minus becomes a plus. Now I have my upper bound. All right, 2.68 to 12.16. So any value beyond 2.68 to 12.16 now we would say is unusual. They're allowing for this to identify outliers. All right, so we could say is an outlier. So therefore, only 21 is an outlier. All right. So no longer the 12, because 12 just very barely fits in that interval. It's right at the very edge of it, but that doesn't matter. All right. And on the low end, we're still in the neighborhood of 3, so I'm not worried about that. 2.68, every number is at least 5, so they're going to fall in the interval. All right. So explain why method A might identify more points as potential outliers than B for a distribution that's strongly skewed to the right. All right. And that's really what we have here. All right. So that was a weird noise. I don't know what that was all about. All right. So we have you're looking at something that is a narrower interval, right? When we're using the traditional outlier approach, than the unusual usual method, all right? So method A produces a narrower interval than method B for a distribution strongly skewed to the right. This allows for more values to be considered an outlier. All right. Now, they only asked about skewed to the right. So we don't have to worry about what would happen if it were a normal distribution or if it were a skewed left. It's just saying focus on skewed right, what's going on. The observation here is one interval is narrower than the other. That's why one of them was able hold on. I just want to make sure I actually answered the question. Method A produces a narrower interval. All right. So yeah, I just wanted to make sure that that was there because it's kind of important that you actually answer the questions being asked. All right. So since it's skewed to the right, you're getting a narrower interval for method A than for method B. Because that interval is narrower, there are more points that will escape that interval and be considered an outlier. Whereas if you had a wider interval, it's going to capture more points, all right, making those points seemingly non-outliers. All right, either way, whether it's contained within an interval or not, that number 12 is right on the bubble anyway. So you're not looking at something that's like, I'm absolutely sure this is an outlier. It should not have been in a data set. There's something wrong with the information that I collected. We don't have enough to say that about 12. We do have enough to say that about 21 because using two different methods, we're able to come up with the same result. All right. So you see, it's not a bad question. When you really dive into what it's asking you to do, it's really not terrible. There really isn't much going on with this one. All right. But your explanations and your attention to detail are going to go a long way. All right. Number 2. Researchers will conduct a year-long investigation of walking and cholesterol levels in adults. They will randomly select 100 adults from the target population to participate as subjects in the study. All right, so it's another part A, part B kind of deal. One aspect of the study is to record the number of miles each subject walks per day. The researchers are deciding whether to have subjects wear an activity tracker, like a Fitbit or something, to record the data, or to have the subjects keep a daily journal of the miles that they walk each day. Describe what bias could be introduced by keeping the daily journal instead of wearing the activity tracker. All right? So this is really just an explanation. If you think about it, the activity tracker is going to be more likely to produce accurate results. All right? The bias is related to personal perception of the amount of walking completed. Now, you kind of stay away from things like, I would say, definitive statements. We wouldn't say it's definitely or likely to be a particular outcome, but we want to kind of couch what we're about to say by saying that, this is just our own thoughts on the matter. And that is, take the thought of people lie about things. All right? You don't want to say a person is more likely to lie about how much walking they've done. All right? You don't want to say that because you don't know that. All right? But what you can say is that there is a susceptibility with this framework for a person, if they're going to lie about how much walking they've done, that this allows for that. All right? So this approach allows the subject to, it's kind of like grammar has never been my thing, but the approach allows the subject to, I don't want to say lies, that seems pretty harsh, but to, and I'm not going to write finagle, it's like they're going to finagle their outcomes. I mean, you get the idea, but it allows them to be less than truthful. When reporting the results. Now, you could get into why that might be the case. Right? Well, anytime there's a human reporting information about themselves, maybe they'll fabricate it. What was your college GPA? 3.908. All right, now, okay, cool. What was it really? I don't know. I got to look it up. Right? So, that was it because I remember it, and I'm also somewhat proud of that. But it's possible. Like, how tall are you? We've done this before. 6'3". That's what I say. Right? But I fessed up. It's really 6 feet and 2.5 inches or whatever it is. I just round up. All right, people, if you're going to be less than truthful about an outcome, it's going to happen when you have the opportunity to be less than truthful. All right, but you don't want to say people are more likely to lie about it. You don't want to say people, like a person in this case is cholesterol and walking. A person is embarrassed about their cholesterol level and they want to make it seem like they're actually doing the exercise, so they're more likely to lie about how much exercise they're doing. You don't know that. You can't say that. Is it a reasonable assumption? Yeah, probably. Right? But you can't put that on paper because they're going to look at that and say, how do you know? Right? So unless you justify that claim, you're going to run into trouble. All right? So they give you a whole page to write your response here. So there is opportunity to elaborate, but yeah. Don't make any claims that you can't substantiate. Oh, also, you'll notice this little thing here. Use a pencil or pen with black or dark blue ink only. Do not write your name. Do not write outside the box. Right? That little simple bit there, don't write outside the box. It seems dumb, but the graders are told that anything that's written outside the box should not be even looked at. Right? You could put a beautiful response, and then right at the bottom, put an additional fact that would get you to a 5 on the exam. It's outside the box. They can't even look at it. Right? So just little things like that, just be careful about. All right. During the course of the study, subjects will have their cholesterols measured each month by a doctor. The researchers will perform a significance test at the end of the study to determine whether average cholesterol level for subjects who walk fewer miles each day is greater than those who walk more miles. So fewer versus more. Selecting a random sample creates a reasonable representative sample of the target population. Explain the benefit of using a representative sample from the population. It seems like the kind of thing where it's like, well, the benefit is that it's going to be better. Like, why would I, like, don't you already know that? You know, if you have a choice between a representative sample and something that's not going to be representative, like, why would you choose something that's not representative necessarily? Right? But they want this is basically a vocabulary question. It's asking you to define what a representative sample means. Right? Representative samples embody the characteristics of the population. And what does that mean? It means the distribution of the sample should be the same. Ideally, it would be the same as the distribution of the population, but we'll take similar, right? So, and what do I, how do I say similar? I say close to the same, or not significantly different, right? So the sample distribution is not significantly different from the population distribution. All right, and when I talk about a distribution, we're talking center, spread, modality, multimodal, unimodal, things like that. So you have enough contained in this word distribution to get the point across. But the more elaborating you do, the better off you're going to be.